Well, good evening. We've got one big night for you on establishing theorems. So let's take the time to get this written out perfectly in our notebook. Although this is a review, this is something that we struggle with the most. So number one is the extrema theorem. Max and min values of the function are called extrema, plural, meaning it can be a max or a min. Sometimes they'll use the word absolute, which we've seen a lot, absolute extrema, absolute max, absolute min, and we know that's when we make our t-chart. But sometimes they'll refer to that as global. Global means the same as absolute. Let f be defined on an interval I containing c. Then two things are true. F of c is the min of f if f of c is less than or equal to f of x, and f of c is the max on f if f of c is greater than or equal to f of x. Now a function does not have to have a max or a min if certain conditions are not met. And that's the whole goal of tonight, is to talk about certain conditions and whether or not theorems apply. Again, one of the toughest things for AP students. So get this first picture sketched out nice and neat, and you'll notice up here I have a maximum, and down here I have a minimum. And another thing you'll take note of is that f is continuous on the closed interval from -1 to 2. So notice when I say closed, these endpoints are completely filled in. They are closed. B. Notice my endpoints are now open. I still have a min, but I do not have a max. So f is continuous, we'll say, on the open interval, and I have a min but not a max. So here we go. A function need not have a max or a min. In my third example, now you'll notice that it's closed again. I have a max, but I don't actually have a min. And take note, g is not continuous on the closed interval. So I guess my question to you is, what seems to be important when you have a max and a min? What is the only time I had a max and a min? Well, hopefully you've said it. It only happens if your function is continuous. And notice not continuous anywhere, because it didn't work here when the interval was open. It has to be continuous on the closed interval. Now, of course, this has a name. Now, most people don't refer to it by this name often enough that it's easy to forget. But I know this appeared on our AP exam last year. The extreme value theorem. If f is continuous on the closed interval, let's get that underlined. It's continuous on a closed interval. Then f has both a max and a min. And that's all it says. It's that simple. If your function is continuous on a closed interval, you are guaranteed to have a max or a min. Okay, so the condition we want to look for is continuous on the closed. Now, perhaps this will help if you kind of circle the C in continuous. Anytime you say continuous, your interval has to start with a C. It has to be closed. So just keep saying that to yourself. Continuous on the closed. So, again, what do we mean by continuous? Well, I know we've taught it, we've already reviewed it once, but let's get it down one more time. F is continuous at x equals a if and only if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, and that has to equal f of a. So sometimes we call that the three-headed monster. In order for something to be continuous, three things have to hold. So if this is a, when I come in from the left, so it doesn't matter what's happening, when I come in from the left and I come in from the right, where they meet has to be a filled-in circle. It has to be continuous. So I can think of three cases in which a function fails to be continuous. What can you think of? Pause it and think for a second. Can you draw something that's not continuous? So one that pops in my head right away is if I have a vertical asymptote. Perhaps I shoot up towards positive infinity on the left and negative infinity on the right. A vertical asymptote will fail to be continuous. perhaps I just come along from the left and I have a great big hole and I move along from the right. So if my graph has a hole in it, it fails to be continuous. The third one I'm thinking is something like this. I come in from the left, maybe I'm closed, and then maybe I come in from the right up here. So again, let's get these sketched in. I would say there are 4 types of discontinuities, and you need to know them by name. So a removable discontinuity, for example, may look something like this, where you have a hole is a good example of a removable discontinuity. Maybe I'm making a parabola, I've got a hole, and I continue on with that parabola. Okay, so a hole is a removable discontinuity. And I think there's 2 ways to represent that. You could have something like, maybe my function comes in, I have a hole, and then there's a closed point up here. So again, this is still a hole, it just has a defined point where this one has an undefined point here. So I would say both of those are holes and they are called removables. A jump discontinuity is kind of like what it sounds. You come in from the left and it jumps up and the graph continues on up here someplace different. So notice this might look similar to this, but this is a hole and this is a jump. It jumps to another part and picks up. An infinite discontinuity, again, think of infinity. It has a vertical asymptote. Kind of shoots up towards infinity, or this could also come down towards infinity. But it has this nice vertical asymptote. So one very important fact to recall, rational functions are continuous over their domain. Anytime you have a rational function, you need to slow down and think about that domain. Polynomials and exponential functions are continuous everywhere. So our next big theorem, I might as well box it in here, is the intermediate value theorem. So right now we've hit the existence theorem. Our second theorem is intermediate value theorem. So you'll notice how this starts again. If f is continuous on what? The closed interval. Notice those C's, continuous on the closed. And f of a does not equal b, then k is any number between f of a and f of b, then there's at least one value c such that f of c has to equal k. And most people are pretty comfortable with the intermediate value theorem. Perhaps in our write-ups we're not, but I can't stress enough, the only condition is that it's continuous on the closed. So here's just a random example. I don't suspect they're ever going to say, hey, use the intermediate value theorem. You're going to have to interpret when it's important to use and what conditions need to be held. So given this polynomial function, and notice the first thing I said was polynomial. That means this is continuous everywhere. Does f of x have to equal 7? Well, think about it. Do you have to have a y value at 7? Well, in order for that to be true, you have to have a number below 7 and a number above 7. And if that's true, then the intermediate value theorem holds. So all we have to do is test our 2 endpoints. We have to evaluate f of -2 and f of 3. So -2 squared is 4. 2 times -2 is -2, and then -1. So f of -2 is 1. Excuse me, f of 3, 3 squared is 9, plus 6 minus 1. So that's really 9 plus 5, that gets me 14. So let's think about this. At f of -2, you're at a height of 1. At f of 3, you're at a height of 14. Do you have to hit at some point y equals 7? Well, since this is a continuous function, in order for me to get from this point to this point without picking up my pencil, I at some time have to cross 7. Could you do it more than once? Sure, you could cross a bunch of times. Could you just do it once? Absolutely. I could make a line like this. The point is that because there's a number below 7 and a number above 7, and this function was continuous, yes, I have proven that you have to have a y value of 7. Let's attack the same question, but does f of x have to equal 19? Well, we already did the math. If my y value here is at 1 and at 14, do I have to hit 19? Well, of course not. Could you? Yes. But the question is, do you have to hit 19? And that answer, of course, is no. I do not have a number below 19 and a number above 19. So here's a pretty common, part C, part D in an AP question. A car travels on a straight road during the time interval 0 to 60. Notice this is a what type of interval? Closed. The velocity is measured in feet per second. Highlight those units to yourself. And has selected values given below. Based on the value of the tables, what is the smallest number of instances at which the velocity could be 20 feet per second? So how many times does the velocity have to hit 20? Now notice, they didn't say, hey Johnny, use the IVT. They're not going to do that. You have to know that if you're trying to prove that this line is hitting 20, you need a number below it and a number above it, and that's the IVT. So let's take a look. If I went from 18 to 25, did you have to hit 20 at some point? Check. 25 to 30? No. 30 to 21? No. 21 to 15? Check again. 15 to 17? No. So right off the bat, I would say twice. Okay, now we know it's the IVT, and the only condition to use the IVT is that your function has to be continuous on the closed interval. So that's literally how I start. Twice. Since, who's your function? Velocity. V of t is continuous, abbreviate there, on the closed interval, 0 to 60. And then if you get stuck, repeat the question back. Then, well, what did you want to know? You wanted to know if v of t equals 20. V of t must equal 20 someplace between 0 and 60 by the IVT, intermediate value theorem. Okay? But what you have to do, what they're insisting that you do on this exam, is that you establish the condition. And the condition is you are continuous on the closed interval. Alright, now the mean one, no pun intended. The big bear here is the mean value theorem. So let's just start with the theorem itself. If f is continuous on the closed, you see how those c words keep going together? Continuous on the closed, but now here's the catch. Something else has to be true. And it has to be differentiable on the open. Okay, so that's the key. Here's our conditions. These two things have to be met. Continuous on the closed, differentiable on the open. Then there exists a number c in between a and b, such that, and we should know that mean value theorem by now, f of b minus f of a equals f prime of c. So, verbally, the mean value theorem says there is a point when the instantaneous rate of change equals the average rate of change, and that's all it's saying, f prime of c. That is your instantaneous rate of change, equals the average rate of change, f of b minus f of a, all over b minus a. Okay, most people love average rate of change. You've done that since 6th grade. Instantaneous is pretty straightforward. You're taking a derivative and plugging in c. Graphically, what does this look like? Graphically, the mean value theorem says there's a point where your tangent line is parallel to your secant line. So let's get a function drawn out. This looks good. The tangent line is parallel to the secant line. So remember, your secant line connects your endpoint. So let's label that secant. And it's saying there's some place where you can draw a parallel tangent. Well, picture this line. Where can you draw a line that's parallel? Just keep moving it up till you find a nice tangent spot. Look, right there. Can it be drawn anywhere else? Here's my parallel line. Can I draw it anywhere else where it's going to hit that curve once? Yeah, right here. So in this case, there's 2 times it happens. Example 3. Let f be this function defined. Determine if the mean value theorem applies. If so, find the c value. Okay, so what do they mean if it applies? Well, what are the conditions? We just went over that. The conditions is it has to be continuous on the closed interval and differentiable on the open interval. So what does that mean? Well, continuous means you're allowed to plug in any number in the world, and it can work. It doesn't have to be pretty, but it works. What's the only number I cannot plug into x? What is the only number you cannot divide by? Well, 0, of course. But does that fall in this interval? No. So I would say this is continuous from 1 to 4. Is it differentiable? Well, heck, you don't know until you take the derivative. So let's rewrite f of x. That's 5 minus 4x to the negative 1. Take its derivative. The derivative of 5 is a constant of 0, so this becomes 4x to the negative 2, and I'll rewrite that as 4 over x squared. Again, is there any number I'm not allowed to divide 4 by? Well, of course there is. You're not allowed to divide by 0. But does 0 fall in this interval? No, so it is continuous and differentiable over this interval. Now, all those conditions had to be met before we apply the mean value theorem. So let's go ahead and apply it now. Get that formula. F prime of C equals f of B minus f of A all over B minus A. Let's do the average rate of change. F of 4 minus f of 1 all over 4 minus 1. Let's do the f prime side. All I have to do is take the derivative, which we just did here. So I'm going to get 4 over, and f prime of c means take the derivative and plug in c. So I'm going to call it 4 over c squared. So let's go ahead and evaluate f of 4. When I plug 4 in this function, I get 5 minus 1. So that's 4. When I plug 1 in, I get 5 minus 4, which is 1, all over 3. So I've got 4 over c squared equals 1. So I get 4 equals c squared. C equals, now don't fall into this bear trap, how many answers do you get? You should get plus and minus 2. Now here's the catch. Your answer has to fall, if you look back at your definition, in between these endpoints. It cannot happen at 1 and it cannot happen at 4. So am I going to keep both these answers? Well, if I have to fall on the open interval, because remember, you're continuous on the closed but differentiable on the open. This is the differentiable side because I took the derivative. I have to fall in between 1 and 4. So I'm going to reject c equals negative 2, and my only answer should be at c equals 2. Alright, I've got one more for us to tackle here. They do say this one is calculator active. They give us function f, x plus the ln of x, for what value of c is the instantaneous rate of change equal to the average rate of change, or the same as. So again, they're not coming out and saying, you know, Connor here, we've got to use mean value theorem. They're not saying that. You've got to interpret it on your own. And that's why you have to understand it graphically. You have to understand it verbally. We have to know exactly what this is saying. So the instantaneous rate of change again is f prime of c. The same, of course, means equal. The same as what? Average rate of change. Okay, so they're setting you up with mean value theorem without actually saying it. Alright, so let's find our instantaneous rate of change. We're just going to take f and find f prime. So that's going to be 1 plus the ln of x is 1 over x. And they say plug in c. So 1 plus 1 over c equals f of 4 minus f of 1 all over 4 minus 1. Now I just broke all the rules. I just need to slow my roll here. I broke everything possible. You can't just assume mean value theorem works until you test to see if it's continuous on the close and differentiable on the open. So boy, did I get ahead of myself. So let's see, is this function continuous? Well, the only time it's not continuous, if I picture the ln graph, is if I'm 0 or less, correct? So if I zoom in on the ln graph from 1 to 4, that is definitely a continuous function. If it's differentiable, again, I already took my derivative because I got ahead of myself. The only number I'm not allowed to plug in here is 0, which doesn't fall in this interval, so the mean value theorem will apply. I've got 1 plus 1 over c equals, let's see, my denominator's 3. F of 4 would be 4 plus the ln of 4. Minus, I have to plug in a 1. So that's going to be 1 minus the ln of, or 1 plus the ln of 1. 1 plus the ln of 1. And I can clean this up a little bit. That's really 1 plus 1 over c equals 4 plus the ln of 4 minus 1. And the ln of 1 we already know is 0, so I don't have to worry about that. So what is that really? 3 plus the ln of 4 all over 3. Now, why do you think they're letting you use a calculator? And if you haven't figured this out by now, you're going to be burned on the calculator section if you don't start getting this down. If two things are equal, how can you solve them with a calculator? You're right, you're just looking to see where they intersect. So I'm not going to actually graph all this out, but you're sticking this in y1, you're sticking this in y2, if two things are equal, and you are looking for that intersection. Okay, so our goal tonight was to quickly review our three big theorems, our existence theorem, our intermediate value theorem, and our mean value theorem. And boy, oh boy, we're going to tackle these in class tomorrow. Have a great night.